Hi there, everyone. Another week, another problem to solve. Let's dive in. A prismatic object is neutrally buoyant 20 centimeters below the free surface, as shown. Object has plane dimensions 1 meters by 1 meters by 50 centimeters deep. Fluids 1 and 2 are immiscible. What is the weight of the object? This is a problem that involves Archimedes' principle and buoyancy. So right away, I would just go to FE Handbook to show you where this is at. I'm going to do a search and I will type Archimedes. And as you can see, you don't have a lot of options, so it's going to get you directly to this page. And what Archimedes' principle and buoyancy is saying, we're going to read point one. So the buoyant force exerted on a submerged or floating body is equal to the weight of the fluid displaced by the body. I have to read that twice and very slowly so you can actually understand what this is saying. So the buoyant force exerted on a submerged or floating body is equal to the weight of the fluid displaced by the body. And two, a floating body displaces a weight of fluid equal to its own weight. Thus, floating body is in equilibrium. What this means is if we have an object, floating object, then the weight of this object is going to be equal to the weight of the liquid displaced by this object. So again, the weight of this object, that's what Archimedes' principle is saying, that the weight of this object is equal to the weight of displaced fluid. And then we have a sentence below here, which is saying that in the case of a body lying at the interface of two immiscible fluids, this is directly applicable to our problem we have today, because we have two immiscible fluids. The buoyant force equals to the sum of the weights of the fluids displaced by the body. So in our case, we have two fluids, which means that the weight of our object is going to be equal to the weight of fluid 1 or displaced, the weight of displaced fluid 1 plus the weight of displaced fluid 2. That's all that it is. So let's go to the problem, and we are going to start working on it and apply what we have talked so far. In the problem, we are given the shape of this object. It's 1 meter by 1 meter by 50 centimeters deep. And we are also given the specific gravity of the fluid. So we have fluid 1 with specific gravity of 107 and fluid 2 specific gravity 1.15. We can work this problem in two ways. We can work with density, right? We can work with densities, or we can work with unit weights. I'm just going to remind you that unit weight equals to the density multiplied by gravitational acceleration. So if we work with densities, because it might be easier, because the density of water is 1,000 kilograms per meter cubed, and that might be easier for us. Or we can work with unit weight of water, which is given in the FE handbook, and I'm going to show it where you can find it. Going back to the FE handbook, I'm going to scroll up here at the fluid mechanics section all the way at the beginning. You are given a few things, and you're given the specific gravity formula, which is unit weight of the fluid divided by unit weight of water, or density of the fluid divided by density of water. And then this is also a very important formula, unit weight, which I already wrote it in our problem, but for you to know the relationship between unit weight and density. And then here is the density of water, also given here 1,000 kilograms over meters cubed, and unit weight of water. it's 981 newtons over meters cubed. Wonderful. So as I said, we can use both. You work directly with unit weight, or we can work with density. Let's go ahead and start. So here I'm gonna write the density of water is 1,000 kilograms over meters cubed, and unit weight of water is 9,810 newtons over meters cubed. And since our answers are given in newtons, I'll just go ahead and use the unit weight of water in this problem. So first things first, what we're going to do, we're going to try and find out what is the weight of the fluid displaced by the object. What is the weight of the fluid? The way to solve that, we're going to need the volume of the fluid first. And the volume of the fluid is going to be equal to the volume of the object. And since we have two fluids, we're going to calculate two volumes. We're going to calculate the volume of fluid 1. Let's call it this way. And this is going to be equal to 1 meter multiplied by 1 meter and multiplied by 20 centimeters, which is equal to 0.2 meters, because it's 20 divided by 100. And this is going to give me a volume of fluid 1 of 0.2 meters cubed. And then the volume of fluid 2, let me correct this a little bit because it looks weird. Volume of fluid 2 is going to be equal to 1 meter times 1 meter times 0.3 meters, and this equals to 0.3 meters cubed. And now if we want to calculate the weight of the object is going to be equal to the weight of fluid 1 plus the weight of fluid 2. That's what Archimedes' principle of buoyancy says. Wonderful. So now let's calculate the weight of fluid 1. Let's continue. Actually, we're going to continue here. So weight of fluid 1 is going to be equal to unit weight of fluid 1 multiplied by volume of fluid 1 plus unit weight of fluid 2 multiplied by the volume of fluid 2. Great. So now we have to calculate the unit weight of these two fluids. From the FE handbook, I'm going to just go back quickly to remind you. In the FE handbook, you are given this formula. Specific gravity equals to a unit weight of the fluid divided by the unit weight of water. And this is the formula we're going to use. So I'm going to say specific SG1 equals to unit weight of fluid 1 divided by unit weight of water. And let's see, this is going to be resulting in unit weight of fluid 1 equals to unit weight of water multiplied by specific gravity of fluid 1. And the same thing from this formula, we can say unit gravity of fluid number 2 is going to be equal to unit weight of water multiplied by specific gravity of fluid number 2. And from here, let's go ahead and substitute. Unit weight of water right here is 9,810 newtons over meters cubed multiplied by specific gravity of fluid 1 is 1.07 equals. And here we're going to say same thing, 9810 newtons divided by meters cubed multiplied by specific gravity of fluid number 2, and we have it as 115 equals. So now we're going to just take our calculators and let's do this equation. Let's solve it. 9810 enter 1.07 multiplied. So in first situation, I am getting 10,496, excuse me, 496.7, and these are newtons over meters cubed. And fluid number 2, we're going to have 9810 1.15 multiplied. This is going to be 12,281.5, and the units are newtons over meters cubed. Now that we have these two components, we can come back here to our initial equation and substitute to find out the weight of the object. This equals to unit weight of fluid 1 is 10,496.7 newtons over meters cubed multiplied by the volume of fluid 1, which is 0.2 meters cubed. And you can notice here how meters cubed with meters cubed go away, and we are going to have our answer in newtons, which is what we want. Sometimes it's helpful to follow the units and check to see if you are working correctly. And moving forward, we're going to have the unit weight of fluid number 2, which is 12,281.5, and these are newtons over meters cubed multiplied by the volume of fluid number 2, and is 0.3 meters cubed. Meters with meters go away, and all we have to do now is just calculate this using the calculators. 10,496.7, 0.2 multiplied. Okay, this is equal to, let's say, 2099.34 newtons plus. And next I'll have 12,281.5, 0.3 multiplied, and the next value is 3684.45, and these are newtons. And it results, I'm going to write here, the weight of the object is equal to, I'm going to add these two together, and I am getting 5,783.79, and these are newtons. I am looking here, I have 5,500. I think I might have made a mistake somewhere. Hold on a second. I'm going to double check. So first, 981.15 multiplied, and then 0.3 multiplied. So I think over here, I'm gonna take this out. This value is 3384.45. Okay, so this is 3384.45, and then if we add to that 2099.34 plus, I'm going to get, let me do this, here you go. I'm going to get 5483.79. Okay, so approximately we're closer to option D. 5,500 newtons. And D is our correct option. There you go. And this is how you solve a problem like that. I hope you found this helpful. If you did, as always, I'm going to ask you to subscribe and give it a like because this helps put this video in front of more people just like you. If you are new to my channel, I have 2 free guides. One of them is called Credential Evaluation. And if you want to evaluate your education in the United States of America, I have put together a free guide with step-by-step on how to do that. Click the link below and you are going to be able to download it for free. If you want the standard integrals guide, same thing, click below and you are going to be able to download it for free. If you have any questions about this video or any other videos, please leave it in the comment section below. I am doing my best to answer to everyone. Don't forget that in order for you to become good at these problems, you have to solve as many problems as you can. Keep up the good work, guys. I will see you next week.